lesson on piecewise functions is specifically for my Algebra 2 students. So our piecewise functions are going to be fairly simple. They're going to have generally 2, maybe 3 parts at the most, and all the parts of the function are going to be linear. So we have 2 tasks today, and the first one is to evaluate a piecewise function, understand what it is and what the directions are saying, and then also to graph the piecewise function. So step is to evaluate the piecewise function. So let's get familiar with what a piecewise function looks like. So this particular piecewise function, mouse to work, has 2 parts. And the first part is the function 3x minus 1. But this is only true if your x's are less than or equal to 4. So the domain is restricted on that particular part of the function. And then the other part of the function is 2x plus 7. But that's only to be used if your x's are greater than 4. So depending on what x value you're intending to evaluate the function at, you'll either look at the top function, 3x minus 1, or the bottom function, 2x plus 7. The first question is in function notation, but it says evaluate the function at 10. That's a way of saying x equals 10 is what they want you to figure out. So since 10 is greater than 4, we're going to be using this bottom function. So 2, but instead of x, we're evaluating at 10 plus 7 would be 27. Now don't bother going to the top function to evaluate at x equals 10 because it actually doesn't exist beyond 4. For the next problem, evaluating the function at exactly 4, if I look at the restrictions on my function, for when it equals to 4, we should be looking at the top function. So 12 minus 1 would be 11. The next function, evaluation, wants you to evaluate the function at negative 2. So negative 2 is less than 4, so again, we're going to be using that top function. 3, negative 2 minus 1 would be negative 6 minus 1, so negative 7. And then 5 halves is, don't be confused about that, that's just 2.5. So, top function again, because it's less than 4. So 3 times 5 halves, ugly, minus 1. So let's see, that's 15 halves minus 1, which if I did common denominators, that'd be like minus 2 halves. So that would be, yuck, 13 halves. I don't think when I wrote that problem I wanted it to be that ugly, but that's right, things happen. So these next few problems are the same thing again. We're evaluating function f, and then function g, and then function h. So it's 3 different piecewise functions. They have nothing to do with one another. You just have to watch the notation for evaluation. So these first 3 problems here are asking you to look at function f every single time. And function f is a very special function because it is considered to be 2 constant pieces. The top function says your function is equal to 3 if your x's are less than or equal to 0, or function would be equal to 2 if your x's are greater than 0. So these first 4 questions, not 3 questions, are going to be weird because the answers are either going to come out to 3 or 2 because of the 2 constant functions. The first question, if it's evaluating function f at 2, well, 2 is greater than 0, so it falls into the bottom function category. So normally I'd say plug it into the bottom function, but that always comes out to 2 for that bottom function. The top function, or the next question, is evaluating the function at negative 4. Well, negative 4 is less than 0, so we're going to be evaluating this at the top function. But again, it's a constant value of 3. So anytime I go to evaluate at that top function for f, it's always 3. Exactly equal to 0 would be the top function. And then 1/2 is greater than 0, so bottom function in that case. So as weird as constant functions are, I think they're weird because they don't require a lot of work, and we don't anticipate that, especially in Algebra 2. All right, so the next 4 questions, we're going to be looking at function g. So function g is, use this top function, x plus 5, if your x's are less than or equal to 3. And then use this bottom function, 2x minus 1, if your x's are greater than 3. So the first question is 7. Well, that's greater than 3. Using that bottom function, 2 times 7 minus 1 would be 13. All right, when x is 0, that would be less than 3, so we're going to be using that top function. So 0 plus 5, which is 5. Negative 1 is also less than 3, So that would be -1 plus 5, which is 4. Should be circling these answers, they get kind of ugly. And then exactly equal to 3 is that top function again. So 3 plus 5, which is 8. Now I'm sure you noticed my use of colors here. When I take my notes for math, and what everyone should do when they take notes for math, is really try to color code things, because I think we've all had that experience where we were sitting through the lesson and it made tons of sense, and then we went to go home like 9 hours later when you finally get out of school and do our homework, and nothing we wrote down makes any sense. So try to get in the habit of taking notes in colors, especially for math. All right, the next question is function h. And there are two parts to function h. 1/2 x minus 4 if your x's are less than or equal to 2. And then 3 minus 2x if your x's are greater than or just greater than -2. So -4, be careful with negatives here, -4 is less than -2, so it's using that top function. So 1/2 times, what did I just do, -4 minus 4. So let's see, that's -2 minus 4, so that'd be -6. For number 10, we're evaluating at exactly -2, so that's got the equal to bar on that top function again. So 1/2 times -2 minus 4. So that's -1 minus 4 is -5. And then -1 is greater than -2. So this time we're using h's bottom function. So let's see, that becomes 3 plus 2, which is 5. And then at 6, that's clearly greater than -2, so bottom function again. 3 minus 12, which is -9. So one of the worst things you can do on a question like this for one of my summatives is, if I give you a function, a piecewise function where there's two components, two parts, and it says evaluate it at x equals 3. Well, if you plug in 3 to both the top and the bottom function, and then give me both answers, that tells me that you know nothing about piecewise functions. So please, please, please don't do that. That would be, leaving it blank, probably the worst thing you could do. All right, now let's talk about graphing. Graphing is kind of a long process, and we're going to have a little list of steps that help us walk through the process, but it's really not that bad. And the way that I'm going to teach you guys to graph on this lesson for this YouTube video, I know 4 different ways to teach this lesson. This is just the one that I found the most effective for the most amount of people. Doesn't mean it's going to be your favorite way of learning it. So, if you watch this and, you're in my class and you actually know me, and you want to see another way of presenting it, I'd be more than happy to do that for you. All right, so the first thing I do when I'm graphing is I determine my boundary line. And my boundary line is where the function is going to kind of split and change to the next function. So if I look at the restrictions, which is right here, okay, see this? That would be my boundary line. And if we have multiple pieces, we're going to have multiple boundary lines. So x equals 1, I would take some sort of a highlighter, and I would kind of mark off with a highlighter, because it's not part of my graph, x equals 1. So that gives me a visual break for my piecewise function. On one side of the half plane, it's going to be this first function, 2x minus 1, because that's less than 1. And then on the right side of the half plane, it's going to be the 3x plus 1, because that's greater than 1. We'll get into what it looks like in a second. All right, so one function at a time. What you're going to do, you're going to determine for this top function 2 ordered pairs. Okay? So if you're going to draw it's going to end up being an array. All you need is a starting point and then another point somewhere else on the array, and then you can connect the dots, basically, draw it in. So what I always want to do is I want to start my ordered pair with the point that is actually on the boundary line itself. So 1 is the boundary line. But notice how this has an equal to bar for the top function? That means that there actually is a point at x equals 1 for this top function. We're going to find out in the next function it doesn't actually exist. It's not that bad, don't worry. All right, so an input of 1, you got to come up with the output. Well, go to your formula. If x equals 1, 2 times 1 minus 1, well, that's 1. So I'm going to be drawing a point at 1, 1. I'm going to call it the blue function, the top function. And now I just need another ordered pair, and you could pick any x value you want as long as it's appropriate for the restriction, right? It says right here, only for x's that are less than or equal to 1. So give me any x value you want that's appropriate that's less than 1. So don't go -20, because look at your graph. It doesn't go to -20. So 0 sounds appropriate. Literally, it could be anything you want. So 0 times 2 minus 1 is negative 1. Now, because we're not on the boundary line, I don't have to ask myself, like, oh, is it an open circle? Does the point exist? The points always exist off of the boundary line. That's not the issue. Okay, now you get to play connect the dots. The function ray stems from the boundary line outwards. So from the boundary line out, that was supposed to connect, you're going to make a ray. That is 1/2 of your piecewise function. So we're going to do all those steps again, this time for the bottom function, which I'm going to now refer to as my green function. So for my green function, I need a t-table where I'm going to come up with 2 ordered pairs. And the first ordered pair I always come up with is the one that's actually on the boundary line of 1. But notice, there's no equal to bar on the restriction for the green function, which means he doesn't actually exist at that function. So I'm still going to indicate the ordered pair, but instead of drawing a point, I'm going to draw an open circle. All right, so let's figure out what happens when x equals 1. So go to your recipe. 3 times 1 plus 1 is a 4. So at 1, 4, you're going to draw me an open circle. So it's a visual beginning for that function, piece of the function, but it's not actually a point. And then one more point, any x value as long as it's greater than 1. So be appropriate because this is your domain that you're given here. So something bigger than 1, let's go with 2. What a novel idea. All right, so 3 times 2 plus 1 is 7. So just a good old point at 2, 7. And then play connect the dots with me from the boundary line outwards. If only I could draw a straight line. Okay, so a couple of things that we look for in piecewise function for algebra 2 is my function should be starting at the boundary line and then going outwards somehow. They should not be on the same side of the boundary line because that would mean I messed up on one of the functions. They shouldn't be like going towards each other in any way. They should be going out of the boundary line. Only one of the functions should have an open circle and the other function should have a closed circle on the boundary line. Because on this boundary line where x equals 1, like if I were going to do that problem, remember we were saying like find the function evaluated at, not 1, positive 1. We would ask ourselves, should I go with the top function or the bottom function? It can't be both. It can't be both at the same time for these. So that's why one of them's open and one of them's closed. So if you're looking for like a step-by-step process, for me, for our class, our first step for this method is to highlight the boundary line. Okay. Then we're going to make a t-table for the first function. And then the first point is on the boundary line. Okay. And then you're going to repeat, right? For the second function. So that's the general overview. And just think about what they should look like. And I kind of step back from my functions every time and make sure that they look appropriate, that the 2 rays are going out of the boundary line. There's only one open circle, one closed circle on the boundary line. These do take a little getting used to, don't they? All right, so step 1, highlight the boundary line. X equals 1 again. Not always x equals 1. Okay, that was supposed to be dotted. Work out. All right, so for my first function, which is 1/2 x, I'm going to do that one in blue. I like to color code these things. I'm going to make a t-table for the blue function, and I'm going to come up with 2 ordered pairs based on that restriction. And the first ordered pair has to be my boundary line. So x equals 1 is the boundary line. Notice there is no equal to bar here. So when I go to plot that point, I'm going to have to draw a little open circle instead of a closed circle for that first boundary line point. All right, let's figure out what happens when x equals 1. If we were to plug in a 1 right there, 1/2 times 1 is 1/2, so 0.5. So open circle at 1.5, 1 comma 0.5. And you can kind of exaggerate them on these graphs because it's a little hard for me to grade if I can't see where you graphed. All right, and then you can choose any x you want as long as it's less than 1. So since I'm multiplying it by 1/2 and I don't really appreciate decimals, I'm going to choose something that's smaller than 1 that will produce like a nice even answer. So I'm going to go with 0. 0 times 1/2 is 0. And remember, if you're off the boundary line, it's always a regular old point. So that, from the boundary line out, is not straight. That is my first half of the piecewise function. Now my next part of the piecewise function, well, let's do it in green. I already have red going on here. Negative x plus 3, I'm going to come up with a t-table for him. And the first ordered pair has to be the boundary line point. And I notice this time there's an equal to bar, so when I graph this first boundary line point, it's going to be a solid circle. But x equals 1, negative times 1 plus 3 is 2. So at 1, 2, regular old point. And then anything greater than 1. So like 2, negative 2 plus 3 is 1. Okay. So from the boundary line outwards, there's your other point, or other ray. So my piecewise function should be stemming off the boundary line. Both rays are going in opposite directions as far as like left and right. Slopes of them don't really matter so much, but looks good to me. All right, so next one, boundary line this time at x equals 3. That's pretty bad, sorry. All right, my first function is x plus 2 for x's that are greater than 3. So for my first function, my blue function, when I'm on the boundary line, that first ordered pair that I'm going to come up with, it does not have an equal to bar right here. So this first point is going to be an open circle. Let's figure out where he's at. So 3 plus 2 is 5. So open circle at 3, 5. And then anything as long as it's greater than 3. So 4 sounds like a good one to me. All right, let's figure out where we're at. 4 plus 2 is 6. Okay. So connecting from the boundary line outwards, there's half of our piecewise function. Our other piece, the green function, when I go to write the first ordered pair, the one that's on the boundary line, it does have the equal to bar in it, which means I get to write a filled in solid point. So let's figure out what that's at. 3 minus 3 is 0. But 3, 0, closed circle. And then anything less than 3 you can plug in. So how about 0? Speaking of 0, 0 minus 3 is negative 3. So ordered pair 0, negative 3, also a point on that ray. From the boundary line, almost outward, connecting the rays. Make sure that the rays are going on opposite sides of your boundary line. One is open, one is closed in the boundary line. I think this looks good. All right, this one's fun. The first function, one of those weird constant functions, okay? So when I go to come up, I didn't do the boundary. Oh, yeah, x equals 1. Okay. You know, when I'm teaching this, like at the actual smartboard in the classroom, I pull out the really cool, like, smart tool. They actually have a highlighter. It's beautiful. Sorry. All right, so the first one, ordered pair. When x equals 1, which is the boundary line, I notice there's a equal to symbol, so we're going to be drawing a closed circle. Normally I'd say plug in a 1. Well, there's no x to input it into because the y value constantly comes out to 2. So 1, 2, and then choose anything less than 1, so how about 0? Same thing. I can't input 0 because the answer is always a 2. So for this part of the piecewise function at 1, 2, and at 0, 2, if you went to go connect these points from the boundary line outwards, and if you could draw a straight line, which I can't, you would see a ray that's going out at y equals 2, which is exactly what the constant function y equals 2 looks like. So the next function is not a constant function. This guy here. So we're going to see a more traditional ray that we've been graphing here. So the boundary line point this time does not have the equal to symbol. You're going to have an open circle on that first boundary line point. Got a little crazy with my brackets there. All right, so when x equals 1, 1/2 times 1 is 1/2 plus 2 is 2.5. So open circle at 1, 2.5. Eek, that's close. And then anything bigger than 1. So I'm going to go with something even because it's being multiplied by a 1/2. I'm going to go with 4. So 1/2 times 4 is 2. 2 plus 2 is 4. All right. So from the boundary line, oh, outwards. You know, one of these days I'm gonna get really good at graphing. All right, 12 years from now. How long it took me to get this good. All right, good. So that was a little unusual because it did have one piece that was constant. Okay, two more. We got this. All right, boundary line this time at 0. So it's a little difficult to highlight the axes if you're using pencil. So I would really encourage you to use a highlighter, even if you have just like an old-fashioned Crayola, like a yellow marker, that works great. All right, the first function is negative x. That is not constant, so we do need to think about ordered pairs here. And the first ordered pair, which is the boundary line ordered pair, has an equal to bar on it. So when I graph it, it's going to be a solid point. So let's figure out what the location is. 0 plugged in gives me 0, whoop-de-doo. And then anything less than 0. So I'm going to go with like -2. So if I plug in a -2 here, negative 2 is going to be a positive 2. And then from the boundary line outwards, connecting and making an array. Same thing for the bottom function. The bottom function is 2x. And then that first ordered pair that we're going to come up with, that x equals 0, because it does not have an equal to symbol right here, we're going to have an open circle. So the location is 0, 0. Now this is weird because normally I'd say like, oh, we'll put a like open circle, but there was already a filled in circle from the original function. This is a case where they overlap each other. And that's okay, that happens. Just keep on going. Okay, anything greater than 0 goes like 2, why not? All right, plugging in a 2, 2, 4. Okay, so this is a case where it's not violating anything. I did technically have one open and one closed circle. They just happen to be at the same point. So obviously a filled in solid circle would kind of override that open circle. And they are stemming on opposite sides, going towards opposite sides of the boundary line. So I feel good. Moving along. All right, 18. Boundary line at 2. All right. So for my first function, which is, let's say this guy, it does not have an equal to bar for that first boundary line point, but figuring out the location at the boundary line, 2 plugged in gives me -1. So at 2, -1, open circle. And then anything less than 2, so I'm going to go 0. I like easy numbers to plug in. 0 minus 3 is -3. And then from the boundary line outwards, connect and make array. Something similar for the bottom function, but we're going to have 2 different ordered pairs probably. And the first ordered pair has an equal to symbol on the boundary line, so it is going to be a solid point. Let's figure out the location. 1 minus 2 is -1. Ah, look at that. And we just saw this in the last example where they end up overlapping and overriding each other essentially. So it's all right, it happens. And then anything greater than 2, I'm going to go with like 4. 1 minus 4 is -3. If I can count, that'd be good. There we go. So that was fun. Those are some examples of types of piecewise functions that we're going to be doing in Algebra 2. They do get a little more complicated when you move on to college algebra and Math 4 and pre-calc because not every function in the world is linear. We have quadratic functions and all sorts of polynomials, just various types of functions. So this is a good introduction to them. And the real exciting part is when we get to go and create the piecewise functions based on the graph, or even more special, based on story problem. Look forward to that.